Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello friends. In this video, we are going to study about the Routh Hurwitz criteria, that how we can make the comment about the stability of a system, that whether the system is stable or unstable using the Routh Hurwitz criteria. So let's start with our topic. Before starting with the Routh Hurwitz criteria, first we will study that what is the Hurwitz criteria to determine the stability. We know that for a control system, the stability, it is always defined with respect to the location of roots of the characteristic equation. So the characteristic equation, it plays a very important role for a control system. So if we write the characteristic equation for an nth order system, it will be like So this is the characteristic equation of an nth order system. Now this scientist Hurwitz, he says that for a system to be stable, the Hurwitz determinants, they should be greater than 0. And these Hurwitz determinant, they are the principal minors of a following arrangement. So if we see that arrangement, it is like so this is the Hurwitz determinant. Okay, this is the generalized form of the Hurwitz determinant. Now we are going to take all the Hurwitz determinant inside in it. Like first we are going to take this A1, then we are going to take A1, A0, A3, A2. So all the principal minors of this arrangement, they should be greater than 0 for a system to be stable. So that was the Hurwitz criteria. So if you write so that was the generalized arrangement of the Hurwitz determinant, and in with this we are going to take different determinants. So first we have taken D1 will be A1 should be greater than 0, then D2 is the arrangement or the determinant of A1, A0, A3, A2, so that should be greater than 0. Just like this we have D3, D4 till Dk. Okay, so all these determinants, they should be greater than 0 for a system to be stable. Now if we see this method, this Hurwitz criteria, this is very time requiring, because you have to first write the characteristic equation, then you have to write this arrangement, then you have to determine all the determinants, and then you will check that whether all the determinants are greater than 0. So determinant of a 3x3 matrix, 4x4 matrix, it is very time requiring. Okay, so this Hurwitz criteria, it was mathematically very complex. So the scientist Routh, he makes some modifications in this criteria, and he proposed his own criteria for determining the stability, and that is known as the Routh stability criteria. So let's study about the Routh stability criteria. We will see one by one all the steps of this criteria, that how we can determine the stability using this method. So first step is to determine the characteristic equation of the system. So characteristic equation of a system is given by 1 plus ds hs equals to 0. Now let's take an example of a characteristic equation. So we have taken an example of a characteristic equation. In this we have the coefficients as a1, a2, a3, a4 and a5, and we have the power of s. The highest power is s to the power 4, then s cube, s square, s and s to the power 0. Okay. Now our second step will be to build the Routh array, and how this array can be made, let's see in step number 2. So this is how the Routh array is made. Let's see. The highest power of s, we have taken this as an example of the characteristic equation. So in this characteristic equation, the highest power of s is 4. So first we are writing s to the power 4, then all the powers s cube, s square, s1 and s0 we have written on the left hand side of this line. Now on the right hand side we are going to write the coefficients. Because the highest power, it is an even number, so we are going to start with the even numbers. Okay, even powers of s. So here we have s to the power 4, coefficient is a1, so here we are going to write a1. Then coefficient of s to the power square, because highest power is even, so we are going to start with the even numbers, even powers of s, that is s4, s square and s to the power 0. We are going to write their coefficients as the first row of this array, a1, a3 and a5. Then these odd powers of s coefficients we are going to write a2, a4. If any of the coefficient is missing in the array, then we will write 0 for that coefficient. Okay. Now s to the power 2. We will write here x1, and this x1 will be determined by multiplying this coefficient a2 with a3 minus a1 with a4 and divided by a2. So this is how x1 is determined. Then we will determine x2, which is we have to multiply the first column with this coefficient a2 into a5 minus a1 into 0 divided by this a2. So this is how x2 is determined. Now further coefficients are not present, so we will write here 0. This coefficient is missing, so we are writing 0 here. Now y1. y1 will be determined by multiplying the coefficient just above it, x1 with a4 minus a2 with x2 divided by x1. Then y2 will be, if we have to multiply this x1 with 0 minus 0 with a2, so the answer will be 0. So here 0 is written. Then y3 will be 0. Similarly z1 will be, we have to multiply y1 with x2 minus x1 multiplied with 0, okay, and divided by y1. So in this way, all the coefficients you have to determine and you have to complete till power of s is equals to 0. So you have to build the Routh arrays in the second step. Okay. So now our next step is step number 3, and in step number 3 we are going to determine that how many number of sign changes are there in the first column of the Routh array. So to check the stability, we will determine the total number of sign changes in the first column of the array. Suppose we have taken this example, and in this a1 coefficient, it is positive, a2 is positive, and x1 it is coming out to be negative. Y1 is again positive and z1 is again positive. So this x1 it is negative. So positive, positive, negative. So there will be one sign change from positive to negative. Then again it is positive. So from minus to positive, again a sign change. So there are two sign changes in the first column, that is from positive to negative and then from negative to positive. So there are total two sign changes. So these sign changes in the first column of the Routh array, they are indicating the number of roots of the characteristic equation which are lying on the right half of the S plane. And if the roots they lie on the right half of the S plane, it means that the system is unstable. So if there is any single sign change in the first column of the Routh array, it means that the system is unstable. So here I have written, to check the stability, determine the total number of sign changes in the first column of the array, and then the number of sign changes, they indicates the number of roots of the characteristic equation in the right half of the S plane, that is they are having a positive real part. Okay, so this indicates that if there is a sign change, then the system is unstable. If there is no sign change, then system is stable. So this is how the Routh stability criteria, it is defining the stability, or it is checking the stability of the system. Now let's see the necessary and the sufficient conditions for this Routh stability criteria. So these three are the necessary conditions for a system to be stable. First is that none of the coefficients of the characteristic equation, they should be missing or they should be zero. Okay, so no coefficients should be missing. Like if we are starting, we have taken the example of the characteristic equation in the Routh's method. In this characteristic equation, all the powers of S are present. Starting from S4, we have S cube, S square, S1 and S0. So all the coefficients are present. No coefficient was missing and none of the coefficient was zero. So this is the necessary condition for a system to be stable, that none of the coefficients should be missing or zero in the characteristic equation. Now every coefficient, it should be real and it should have same sign. So no coefficient of the in the characteristic equation, it should be imaginary, all should be real, and also they have same sign. If one either they should have all positive sign or they should have negative sign. Okay, so the sign of the coefficient should be same, they should be real, and no coefficient should be missing and zero. Now third necessary condition is that if the characteristic equation of the system, it contains only odd and or only even power of S. Like take an example, if we have S cube plus 4S1 equals to 0. So we have only two coefficients, like only odd power of S are present. And if we take an example like 2s4 plus 3s square plus 1 equals to 0. So only even powers of S are present. So if this is the case, then it indicates that the roots of the characteristic equation, they have no real part and they have only imaginary part. Okay, so these type of characteristic equation or these types of systems, they have no roots in the real part. The roots will have no real part, they will have only the imaginary part, and it means that the output response of the system, it has sustained oscillations. Okay, so these are the three necessary conditions for a system to be stable using the Routh stability criteria. Now what is the sufficient condition for it? So the sufficient condition of defining the stability in the Routh stability criteria is that each term of the first column of Routh's array, it should be positive and it should have the same sign. If all the coefficient or all the terms in the first column, they will have the same sign, then there will be no sign change in the first column, and no sign change means that the system is stable. So the sufficient condition for a system to be stable is that the first column, each term of the first column of Routh's array, it should be positive and it should have the same sign. Okay, now there are some limitations in this Routh stability criteria. So let's see these two limitations, that how these limitations can be solved while checking the stability for a system. Now, first limitation in this Routh's stability criteria is that if in the first column we are getting a term which is 0, then how we are going to solve such kind of problems? So, first limitation will be Now the first limitation we have is when first element of any row is 0 and the same remaining row contains at least one non-zero element. So when we are building the Routh array, we are encountering a situation when the first element of a row, it is coming out to be 0 and this row is have at least one non-zero element. So how we are going to solve such problems? Let's have in the Routh array which we have built up. This was the example which we have taken and we have seen that how the Routh array is built. Now in this Routh array, if suppose this x1 it is coming out to be 0. So this is the first element of this row and this x2 it is non-zero and this is again 0. So this row it is having at least one non-zero element and first element is 0. So this is the situation which we are taking in this first case. Okay. Now such type of situations, they can be solved by two methods. First method is we will use s equals to 1 by z. So this is our first method in which we will use s equals to 1 by z. We were having the characteristic equation in terms of s. So in that characteristic equation, we are going to replace s by 1 by z. We will get the characteristic equation in terms of z. Now we will determine fz. And we will repeat the same Routh array calculations and then the sign change what we were doing for f of s. Okay, so we were having the characteristic equation earlier in terms of s here. Now if we are having that situation that first element is 0, then what we are going to do, we will replace this s by 1 by z. So here we will get a1 1 by z to the power 4 plus a2 1 by z to the power 3 plus a3 1 by z to the power 2 plus a4 by z plus a5 equals to 0. Then we will simplify that equation and we will get fz. And then we will repeat the same steps. We will build the Routh array. Then we will check the number of sign changes in the first column. So same procedure will be repeated for f of z. So this is the first method to resolve this problem. Second method is we have got 0 as the first element in the row. So that 0 will be replaced by a small number epsilon. Okay. So our second step will be replace 0 okay. So 0 will be replaced by the small positive number epsilon and then we will complete the array, Routh array we are going to complete. With this number epsilon. So we are going to replace 0 by epsilon. Then we will complete the array by using this number epsilon. The array will be completed. And then we are going to check the sign change by taking the limits epsilon tends to 0. So let's take an example so that this will be clear to you. So this is the characteristic equation of the system. Now we are going to build the Routh array from it. So Routh array will be the highest power of s in this is 5. So we are going to start with s to the power 5. Then 4, 3, 2, 1 and 0. Now the coefficient of s to the power 5 is 2. Then the next odd power is s cube. So we will write its coefficient. So 2, 6 and then 1. Now s to the power 4, so we will write s to the power 4 coefficient, s to the power square coefficient and s to the power 0 coefficient. So it will be 1, 3 and 1. Now we will determine s to the power 3 coefficient. By this x1 we will determine 1 into 6 minus 3 into 6 divided by 1. So this is 6 minus 6 divided by 1. So it will be 0. Now next we have 1 into 1, that is 1 minus 2 and divided by 1. So it will be minus 1 here. And next we will have 0. So this we have encountered the condition that first element it is coming out to be 0 and this row has one non-zero element. So what we are going to do, we will replace this 0 by epsilon, a positive number. Then we are going to build the rest of the Routh array by using this positive number. So epsilon into 3 epsilon minus 1 into minus 1, so it will be plus 1 divided by epsilon. So S will be 3 epsilon plus 1 upon epsilon. Then next we will have epsilon into 1 and 1 into 0 upon epsilon, so it will be 1. Next we will have 0. Then s to the power 1. We will multiply this with minus 1, epsilon with 1 divided by this. So we are going to get this number as minus of So what we have done, we have multiplied this 3 epsilon plus 1 upon epsilon with minus 1. So this is the term. Then minus of epsilon multiplied with 1. It will be epsilon divided by this term. So this is s to the power 1. Then rest we will get as 0 and 0. Again we will have this term multiplied with 1. This term multiplied with 0 divided by this. So we will get it as 1. 0 and 0. So we have obtained the Routh array in it. Okay. So now we are going to check the sign changes in this first column of the Routh array. How we are going to check the sign change? We will take the limits epsilon tends to 0. So if we apply here the limits epsilon tends to 0, then its value will come out to be limits epsilon tends to 0 on 3 epsilon plus 1 upon epsilon. So here it will be 3 into 0 plus 1 upon 0. So it will tend towards positive infinity. Okay. Then we are going to apply the limits on the term minus Now if here we will put epsilon equals to 0 tends to 0, then it will become 1 upon 0 minus 0 upon this is again 1 upon 0. So this will come out to be a negative number. Now in this Routh array, if we take 2 is positive, 1 is positive, then it is a positive number, epsilon it is a small positive number. Then 3 epsilon plus 1 upon epsilon, it is coming out to be positive infinity. And then this term it is coming out to be negative. So from positive infinity to negative, it will be a sign change. And again from negative to a positive 1, it will be a sign change. So here we are having two sign changes. So two sign changes means the system is unstable. So we are getting the system as unstable because there are two sign changes, so two roots are lying on the right half of the S plane, so the system will be unstable. So in this way, when you encounter the situation that the first element of any row, it is coming out to be 0, and the rest of the elements, at least one of the element, it is non-zero, then either you can put S equals to 1 by Z and you can follow the same procedure, or you can replace 0 by a small positive number epsilon, and then you can follow this method. Now the second limitation is in this Routh Hurwitz criteria is that when all the elements of any of the row, it is coming out to be 0, then what you are going to do? You are going to form a subsidiary, or you can say auxiliary equation. Okay, then you are going to differentiate that auxiliary equation and then equate that auxiliary equation to 0, and then you will get the value of the S. Okay, so let's take an example. So this is the Routh array. We have S4, S3, S2. We have the coefficients here. When we are calculating the coefficient, then this S2 is S square row. This row, all the elements are coming out to be 0. So we are going to form the subsidiary or the auxiliary equation. This auxiliary equation is AS equals to, we have A2 S cube plus A4 S to the power 1. Because here we are having the coefficient of S to the power 4, S square and S to the power 0. Here we are having S to the power cube, S to the power 1. So this A2 multiplied with S cube plus A4 multiplied with S1. So this is the auxiliary equation. Now we are going to differentiate this auxiliary equation with respect to S. So DAS by DS, it will be, here we are having S cube, so it will be 3A2 S square. And here we are having A4 S1, so it will be A4. So now we have got the coefficient of S square and S to the power 0. S square coefficient is 3A2 and S0 coefficient is A4. So we are going to use these coefficients. We will place it here where we have obtained x1 equals to 0 and x2 equals to 0, and then we will follow the same procedure. We will build the rest of the Routh array, and then we will check the number of sign changes in the first column of the Routh array. So when you got the situation that all the elements of the row are coming out to be 0, then form the subsidiary or the auxiliary equation and then differentiate with respect to S, and then these coefficients use it in the Routh array where you have obtained 0, and then repeat the last procedure. So in this video we have studied about the Routh stability criteria, that how we can make a comment about the stability of a control system, whether it is stable or not stable, using the Routh Hurwitz criteria. You have to just use the characteristic equation, then form the Routh array, and then check the number of sign changes in the first column of the Routh array. So I hope that this video is clear to you. Thank you.